Hello, everyone, and welcome to another wonderful day of quantum mechanics. So far, we've been building up the idea that light behaves both as a particle and as a wave. We built up the idea of a photon, which is essentially a quantized packet of light that has wave-like behavior. However, today we're going to discover that while light behaves as a particle and a wave, it turns out everything else does too. So this was essentially first kind of conclusively proven in 1925 by the simple idea of shooting an electron beam at a metal surface and then watching carefully the diffraction pattern as the electrons hit off the surface, diffract essentially along the grooves of the exterior surface, which has the the effect of diffracting the electrons in the same way as if they were waves, giving an interference pattern, which again is a wave-like behavior. Now, this was pretty conclusive evidence that it turns out electrons act as waves because they can give these interference patterns in the right conditions. However, further research showed that it turns out while electrons behave as waves, pretty much every other particle does as well. So all particles have wave-like behavior with a characteristic wavelength given by what's called the de Broglie relation, where the wavelength of a particle is given by Planck's constant, which again is a constant, and the momentum of the particle. So again, as a nice physics refresher, the momentum of a particle can be given by the mass of the particle times its velocity. So we can essentially combine these relationships, and what we find is that the wavelength can essentially be given by Planck's mass and uh, and the velocity of the item. Well, one of the important things that this does is it gives us a way to have an object that travels as a wave with a very controllable wavelength. So one of the classic implications of the de Broglie wavelength actually again comes in the idea of spectroscopy. So one of the problems that we have is with typical spectroscopy is that it's hard to essentially see an object uh, using a particle or light where the wavelength of the light is greater than the size of the particle, which means using visible light, I can only really get resolution down to say about 400 nanometers. So if I want to see any kind of molecular level property, 400 nanometers is way too big. I need much smaller light. So light won't work. So what we can try and do is use a different kind of wave. So one of the classic answers to this is the electron microscope. So you'll essentially have an electron source, which you'll essentially first select for a particular wavelength, shoot it at your object, and then using the diffraction patterns, you can essentially get a good evaluation of the object that you shot at. And again, this is all based on the wavelength of the object. So what we can quickly find is using the Broglie wavelengths, we find that if I have a large, fast object, this is going to give me a very small wavelength or high resolution. So an electron is much heavier than is infinitely heavier than a photon. So if I give a decent velocity on it, I can have a pretty good resolution. However, if you want to increase the resolution a little bit more, you can use, say, a neutron microscope, which does run into the problem that a neutron is much bigger than an electron. So that does give some size limitations. But more importantly, it's also much more massive, giving increased resolution as it's a much smaller wavelength. Then if I slow the object down or essentially make it very light, this is going to give me a much longer wavelength. So we can often use this to do things like try and figure out what would be the wavelength of, say, a scanning electron microscope, which accelerates its electrons to about 2 kilovolts. So one of the first things we want to try and figure out is how much energy is in an electron that's been accelerated to 2 kilovolts. Well, from here, we can just say, well, if I've got a single electron with 2,000 volts, that means it has 2,000 electron volts. So I can then turn that into joules. Using this, I can try and relate my energy with my momentum using the mass of an electron, manipulate the system a little bit, try and get to the momentum of the system. So I now know the energy, I know the mass of the electron, momentum should be fairly straightforward. Though watch out, momentum does give slightly weird units, in this case, kilogram meters per second. Then I can go ahead and convert this momentum into wavelength using the de Broglie relationship. So using this relationship, I can find out that this electron would have a resolution or a wavelength of about 0.27 angstroms. However, in practice, because of how the instrument is set up, electron microscopes really can't beat 1 angstrom. The 1 angstrom is way better than you get out of a light microscope with about 40 angstroms. So it's a good improvement. So again, this is one practical use of the de Broglie wavelength. However, in practical purposes, one of the reasons why we're really going to care about de Broglie is that it shows that all particles exist as waves, because if all particles have a wavelength, that means they all have wave-like behavior. And this is going to become a big push going forward, is we need to try and figure out how we can describe the behavior of subatomic particles using wave mechanics. So anytime I've got a small object, so specifically those found in an atomic scale, they're often going to be way more diffuse and way more delocalized than we'd expect from classical mechanics. So this means that if I'm going to describe an electron, a neutron, a proton, I'm going to need a new set of equations that describe both particle and the wave-like behavior of these systems. And this gets a little bit messy. And this is one of the sources of the reputation of quantum mechanics, is we need to try and internalize this idea that particles don't exist at one point in space. They're very fuzzy, they're very diffuse. One of the ways I like thinking about it is that most particles act like a dust bunny. There's a certain amount of mass. If you pin it down, it's in one discrete location. But if you just look at it across the room, well, it occupies way more space than it has any right to. And to a certain extent, that's one way to look at matter, especially when you're working on the subatomic particle. Everything's a little bit more diffuse, so we have to worry about wave mechanics. So the equational form we use to describe these particle waves is called the wave function. So this is essentially a mechanical or an equation that essentially shows the relative probability of finding a system in a given position in an XYZ field, so good old Cartesian coordinates. And then we have to acknowledge the fact that it isn't going to be stationary. There is going to be a time-dependent component. So this is going to be a bit much for us to tackle. So we're going to try and tackle this one dimension at a time. We'll look at a 1D system in X. We'll slowly introduce Y and Z. And we're going to be avoiding time-like behavior like the plague, because it's hard and this isn't a physics class. So we're going to be trying to give an equational form where we can describe our system, again, as a wave, and what that means in practical sense. So next time, we're going to dive a little bit more into wave functions. Till then, take care.